Hello everyone, and thank you for joining me. My name is Lauren Barrett. I am a winemaking specialist here at Enartis, and today we're going to be focusing on driving Pinot Noir style for yeast selection. This is a re-recording of a webinar that was recently took place, so I don't need to go over some of the webinar formalities, and then some of the poll questions won't be included. But to get started on the bulk of the presentation, I first wanted to focus on Pinot Noir characteristics and clonal variation, go over some of the various styles of Pinot Noir, the phenolic and aromatic composition found in Pinot Noir, and then also some processing techniques. The majority of this presentation will be focusing on yeast characteristics in Pinot Noir from our range, sharing some of our chemical and aromatic data, and then also summarizing and concluding our findings. There's a lot of really rich content and citations in this presentation, and as I'm limited on time, I can't dive into as much detail as I would like with some of these other subjects, but I highly recommend referring to this as a reference and also taking a look at the citations page and following up with some of those cited references as well for further information. So just a few definitions before we get started. A grape variety is a group of morphologically distinct clones originating from a single initial seed which was sexually produced. Now this is different from what is a clone, which is a select cutting from a parent plant that is vegetatively propagated. Now, majority of grapevines are propagated in this way, as it's very difficult to establish a vineyard from a seed itself, and it takes a very long time for that seedling to reach maturity and fruitfulness. So almost all of the grapevines that you see are from clonal propagation. Now, a genome is an organism's complete set of DNA, and it's including all of its genes. Genotype is the genetic makeup of an organism, describes the organism's complete set of genes through nucleotides. And a phenotype is a collective expression of the genotype in conjunction with the environment and the observable characteristics that we see. Now, it's important to talk about the Pinot Noir genome because it can really give us insight into the divergence and evolution of Pinot Noir, and also give us clues into specific genes and clones which might be resistant to disease or might increase color or wine quality parameters. So in 2007, the Pinot Noir genome was sequenced, and it was found to have 19 chromosomes with a relatively small genome compared to other crops, with a very high degree of heterozygosity. And now this means that there is a very high variation and substitution in some of the single base pairs of DNA, which are nucleotides, found within its genome, which means that there is a lot of chance for mutations and variability to arise. And so this brings us to what we're all familiar with is, of course, kind of some of the different Pinots: Pinot Noir, Pinot Gris, Pinot Blanc, Pinot Meunier. What makes these different? And a lot of these differences and divergence are arising from somatic mutations, which lead to a phenotypic divergence. So here we have a picture of Pinot Noir on the right-hand side. This is the apical meristem, which is a point of growth and differentiation of various cells. And what happened here was between this L1 and L2 meristemic layer, there was a somatic mutation which yielded this hairy phenotype, which we can see below on the shoot tip of Pinot Meunier, and caused a divergence from Pinot Noir to Pinot Meunier. And this Pinot Meunier was selected and propagated and is now widely used throughout the world for sparkling wine production. Now this image actually comes from a very fascinating picture, just kind of a side note. And it was published from Anne Pellegrino and Laurent Tarragosa, and this was focusing on actually a specific mutation of Pinot Meunier, and it's the microvine, which unlike grapevines who have an annual fruiting cycle, the microvine is continuously fruiting. And so it really is a valuable tool for boosting grapevine studies in physiology and genetics. So please check out this article listed here and in the citations if you want to learn more about grapevine genetics. So why are there so many different clones of Pinot Noir? Well, the older variety is, the more mutations it is likely to have. So a lot of these mutations are then culturally selected and propagated. And from there, since Pinot Noir is potentially one of the oldest cultivated varieties, it was first just thought to be described by the Romans in the 1st century, that gives rise to all of its variations in different clones. So with the potentially thousands of different Pinot Noir clones that are out there, they can be categorized into 4 main groups, and that being standard quality, high fruitfulness, upright shoots, loose clustered, and I wanted to focus on the main North American examples. So in the 1950s, we saw an influx of Pomard clones, specifically to UC Davis. Here we have UCD4, which was one of the first academically available Pomard clones from UC Davis. And then we also see a surgence of what is been coined as suitcase clones. And a lot of these suitcase clones are also known as heritage clones, such as Swan and Martini and Chalon, and they were actually selected from cuttings in France and then illegally brought here to the United States. Dijon clones in the 1980s had a much more of a resurgence, with now over 50 registered with the FPS, which is Foundation Plant Services. And majority of producers like to plant a mixture of these different clones to try to create a complex wine with different clonal characteristics. And here, just on the right, you can see some pictures of just the varying cluster size that you would expect to see with the different variations of Pinot Noir. Now, Pinot Noir has such a wide spectrum of different wine styles, so it's hard to categorize, but we can really focus on putting it into 2 groups, and that being Old World and New World. And Old World, of course, is stemming from Burgundy, which is the birthplace of Pinot Noir. And this style is really drenched in tradition, history, and culture. These wines characteristically have lower alcohol. They're less extracted than New World wines, higher acidity, as it's typically applied in cooler growing regions. These producers are experimenting with a higher portion of stem and whole cluster inclusion, and barrel aging can occur for about 18 to 36 months, depending. A lot of the specific yeasts that are being used are select isolates from Burgundy, or producers are just practicing spontaneous fermentation. Some challenges that can arise with these wines is that they can be too thin, they can be reductive, herbal, green, and tight. Here are some common descriptors for Old World Pinot Noir, that being animal, mushroom, red fruit, spice, and some herbal characteristics as well. Here we have just a few pictures from Burgundy, actually. So we use Clos Vougeot, and here is a picture of an older cellar with some oak vats, oak open-top vats, which would have been used for vinification, and then a very old plate press, which is located in the back. In France, remontage means pump over, and pigeage means punch down. And what we see here is feet, and historically, and still today, many producers are actually practicing cap management with actually getting into the tank and punching it down with your feet. This is a Hospice de Beaune, which is a very historical and iconic establishment in Beaune, and they hold an auction every year, which is very famous throughout the wine world. And they also have various stakes in many vineyards located throughout the region. Domaine Conferrand is a classic example of Old World Burgundy. It's using 100% whole cluster and spontaneous fermentation techniques. Now, New World, on the other hand, is typically applied for warmer growing regions, but with the exception of Tasmania, New Zealand, and Oregon. And these techniques, for me, stem kind of more innovation, technology, and marketing. they're characterized as having much higher alcohol, higher extraction, lower acidity, they're much more fruit forward, and have a higher oak extraction. And producers are really looking to increase color and phenolic extraction. And a lot of producers are also applying cold soak and using heavier toast barrels, more technological yeast strains, and then some of the challenges that these winemakers face is that these wines can be too alcoholic, they can be reductive, and there could also be a lot of unstable color due to the phenolic profile of Pinot Noir, which we'll get into. So even though this could be coined as a new world, this picture here is actually of a conveyor system with liquid nitrogen sprayers. So the fruit actually gets coated with liquid nitrogen as it's passing through this tunnel. And this picture was taken in Burgundy. So it just goes to show that even though Burgundy is considered an old world producer, they are still at the forefront of a lot of these innovative technologies which are coming out nowadays, as well with the Flash de Temps, which is mainly Bordeaux, but Flash de Temps is also applied for Pinot Noir and thermovinification pictured here. In the top right-hand corner, this is a picture of Anna Carew. She is a researcher from the University of Tasmania, and she's been doing a lot of interesting research with microwave treatment, and I highly recommend checking out her dissertation, which is listed in the citations, if you want to look into more of some of the innovation with maceration techniques with Pinot Noir. Now I wanted to touch a little bit on Pinot Noir and its regional differences and its aromatic profile between Burgundy, the West Coast, and New Zealand. And we have some different compounds that are listed here, but more importantly, I wanted to point out that beta-damascenone is found in all three of these types of wines. And it's beta-damascenone is a C13 rescinoid. It's formed from the degradation of carotenoids, and is found in almost all grape varieties. But unlike other neuracipinoids, it actually increases with shading. So there's a lot of research with Pinot Noir shading and then also with NPK nutrient supplementation. But it's an important impact odorant and aroma enhancer. And it has aromas of floral, honey, tea. It's an important compound that we'll touch on later with some of our aromatic profiles with our yeast range. So Pinot Noir actually lacks acylated anthocyanins. So the dominant anthocyanin in Pinot Noir is the malvidin-3 glucoside, which is actually very temperature sensitive. So that's important to keep in mind with Pinot Noir fermentations, and could shift it to its colorless chalcone. But even though it has a high concentration of C tannins, these C tannins have a very low extractability, and that's due simply to the skin to seed ratio. And Pinot Noir color is described as being garnet, even though there's quite a bit of variability as many producers are blending with Syrah and other varieties, and there's also some clonal variation with that color profile as well. Now I wanted to touch on Pinot Noir processing, even though I don't have as much time to go into each individual step, but important considerations for elaborating Pinot, at least, would be the consideration of whole cluster inclusion and whether a portion of destemming, and if you're leaving that whole berry, if you're crushing it, or if you're adding back any of the stems. Many producers are applying a cold soak maceration in order to, the school of thought is thinking to extract more anthocyanins and tannins, but there's been some very promising and interesting research coming out from Federico Casassa and many other researchers, which I highly recommend checking out. This article. It was recently published in the American Journal of Enology and Viticulture, and it was very much a hot topic at AACV last week. And I don't have as much time to go into it here, but I definitely recommend checking out this citation. And our focus today is going to be on yeast selection, specifically for elaborating Pinot Noir. So it's important to consider the reality and logistics of making Pinot Noir and considering yeast selection with that. And earlier on in the season, we are going to want a yeast strain that is a fast finishing fermenter with low nutrient requirements, There's going to be a lot of turning of tanks. It's a stressful time for winemakers. We don't want anything that is going to have a slow or lag fermentation. Some regional considerations are cool climate. With cool climate Pinot Noir, you might not be picking at the optimal ripeness, so you're going to want to be picking a yeast strain to increase mouthfeel with high glycerol production, and then also reduce acidity, so maybe a yeast strain which can consume some malic acid. Now in warmer climates, on the other hand, we want kind of the opposite, so we want to retain acidity by selecting a low malic consumption yeast strain. And then also there's a specific acidulating yeast strains which can be applied as well. And with warm climates, there is a much higher alcohol potential, so selecting a yeast strain with a low conversion rate from sugar to alcohol is desirable, and also high glycerol producing strains as well, as that metabolite takes away some of the ethanol production. And of course, Pinot Noir, it's a very finicky and sensitive grape variety to many different diseases and viruses. And so botrytis and powdery mildew are very common with the variety, and it's important if there's any incidence of infection to be using a robust, low nutrient requiring strain that most importantly will quickly finish fermentation. So now we're going to be diving into some of our yeast characteristics in Pinot Noir. So here we have the comparison of yeast strains within our portfolio. We have ES454, ES488, WS, MB15, Aspenhausen, Vintage Red, and a new strain in our portfolio, U42, which is a Saccharomyces uvarum. Now we are using for this fermentation, this Pinot was from the north of Italy, from the 2017 vintage, had a potential alcohol of 14.3% and a pH of 3.74. All of this was done in fermentation flasks at the lab scale, so everything was manually destemmed and crushed, homogenized. There was no addition of SO2 or nutrient addition, and temperatures were conducted at 20 degrees Celsius. So now we're going to be diving into some of the main chemical parameters that we found with these fermentations. Here we have a fermentation curve, and this is actually going off of the loss of grams of CO2 per 100 mils of juice and the days. So what we can clearly see here is that in red, this is the wild or spontaneous fermentation that was conducted, and it had the slowest fermentation kinetics compared to the rest of the portfolio, which all seem to finish relatively a day or two earlier than the wild fermentation. The second slowest fermenting looks like it's the Aspenhausen, which for those people who have used Aspenhausen in the past, this is a characteristic of the yeast, and it is a kind of a longer fermenting yeast. Now we wanted to share some alcohol and sugar conversion data. All fermentations went dry, as we could see earlier in the previous slide. And what we found was that within our portfolio, Vintage Red and MB15 had a low yield of sugar and alcohol, which compared to, let's look at the ES488, which is at 14.6% alcohol. That's a difference of almost 0.6% and then 0.4% with the Vintage Red and MB15. And then U42 had the overall lowest yield and sugar and alcohol ratio with 13.9% alcohol, which was a 0.7 difference between the highest, which was the ES488 again. So if you were actually looking to elaborate a wine with lower alcohol, Vintage Red, MB15, and U42 application would be a good tool in doing so. And then on the opposite end, if you were looking to increase alcohol, ES488 would be a good candidate for doing so. Here we have some color characterization with the various yeast strains looking at color intensity and hue. So comparing the yeast strains, ES454 and Vintage Red produce wines with the most intense color and hue, with vintage red increasing 30% more intensity and hue than the spontaneous and wild fermentation. This is an important consideration for those who are applying spontaneous fermentation and who are also wanting to increase color characteristics, as it might be useful to use some of these pure strain culture techniques, especially with vintage red and ES454. Now we're going to be examining some of the glycerol production within our portfolio that we examine in these fermentations. And U42, the Saccharomyces uvarum, produced 40% more glycerol than the lowest producer, which was actually Aspenhausen. And for those people who are looking for more Cerevisia strain, ES454 produced 11.3 grams per liter. And glycerol is a very important compound in wine. It's has a effect if it's 10 grams per liter or more on the viscosity and mouthfeel of wine, and is an important contribution to the overall sensory perception of other volatiles. So for those producers who are looking to increase mouthfeel and smoothness, applying U42 and ES454 would be good candidates for trying to get that characteristic in your Pinot Noir. Here we have acetic acid production, which is always important parameter to consider when selecting yeast. And U42 produced the lowest acetic acid in comparison to the spontaneous wild fermentation, which was at 0.66. So the average content in the trial was at 0.29, with all of the other strains in our portfolio producing lower amounts of acetic acid. The Aspenhausen, again, because it is a longer fermenter, had a slightly increase in acetic acid production. Acetaldehyde is an important compound in wine and helps with color stability. It creates acetaldehyde bridges and can catalyze condensation reactions for stabilized color. And we saw this with the vintage red and ES454 in the colorimetric data, which was presented before. And it's with no surprise that vintage red and MB15 were actually medium to high producers of acetaldehyde. And we have Aspenhausen here as being the highest producer of acetaldehyde, but it's important to note that the long fermentation kinetics of Aspenhausen could be, this buildup of acetaldehyde could be due to the oxidation of ethanol as well. So for those who are looking for higher acetaldehyde to increase color stability, vintage red and Aspenhausen and MB15 would be good candidates for doing so. Now we wanted to look at yeast effects on wine acidity, and what we found was that U42 produced the highest levels of succinic acid, and succinic acid can contribute to the total acidity of wine and is also connected with minerality in wine. And then the ES488 consumed the highest level of malic acid, which is presented here. And for those people who are trying to reduce acidity in cooler regions, this would be a strain which would help reduce some of that malic acid and reduce acidity. Now we have some analysis looking at the SO2 production and ethyl acetate within the various yeast. And ethyl acetate is normally a positive aroma enhancer in wine. It's usually present between 30 to 60 milligrams per liter, but anything above 150 milligrams per liter is considered a defect. And so here, U42 produced the lowest amount of ethyl acetate, and with no surprise of wild fermentation, produced the highest level. Now, in total SO2 for all the strains was a low SO2 production, which is also important to consider when you're trying to elaborate low SO2 wines, and then also thinking about malolactic fermentation and SO2 sensitivity with malolactic bacteria. Now we're going to be looking into some of the main aromatic compounds that were quantified in our fermentations. And so Pinot Noir, the main varietal aroma is arising from non-volatile varietal aroma precursors, which are present as unsaturated fatty acids, phenolic acids, varietal thiols, and majority of these neurosaccharides and terpenes are present as glycoconjugates, so they're actually bound to sugar. And it's important that if we want to reveal these aromatic compounds, that they be released from the sugar molecules so they are volatile and perceived aromatically. So there is a biochemical reactions and then also biological transformations which reveal these aromas, and it depends on the glycosidase activity of various yeast and also bacteria. So it's important to keep the ester activity in the back of your mind when considering yeast strain selection, especially for enhancing some of these aromatic compounds. So we analyzed for benzaldehyde cyanohydrin, which is responsible for this cherry almond aroma, and it's very typical in cool climate Pinot Noirs. And what we found was that U42 actually produced the highest level, almost 48% more than the lowest producer, which was our MB15 within our portfolio. Now, esters are produced via fermentation, a fermentation aroma compound by yeast, and it's responsible for this young kind of fruity aroma in young wines. And they're relatively unstable, but it's important consideration for elaborating young wines. So ethyl esters of fatty acids are more stable over time than esters of acetates, and the only acetate ester that was above the threshold in our fermentation was isoamyl acetate, which is a classic banana kind of candy aroma. And ES454 and ES488 produced overall the highest total level of esters, the highest level odoractive value of esters in our trial. And this is a good tool for producers who are looking for elaborating young Pinot Noir wines, or Pinot Noir maybe more in a carbonic or Beaujolais Nouveau style. And now we're kind of going back to some of the primary varietal aromas, and again touching on beta-damascenone, which we spoke earlier on. And with our trials, ES454, Vintage Red, and MB15 both expressed higher concentrations, or revealed higher concentrations of beta-damascenone. And this is a really great tool for producers who are really trying to drive more of that honey, rose, tea aromatics, and really increase and enhance aromatics, as beta-damascenone is an important aroma enhancer in Pinot Noir. So just to conclude and go over everything and summarize it in a much more easy to digest table, we have this table that we've designed with aromatic and stylistic objective, and it's a good reference for those who specifically are looking to drive, say, a fruity aroma Pinot Noir. ES454 and 488 would be good candidates for that, or driving floral aroma U42 and WS. Fruity and varietal aroma Vintage Red would be a great candidate, and varietal aroma MB15, Aspenhausen. Increasing color intensity and stability would be ES454 and Vintage Red. For those who are in a warmer climate and looking to reduce alcohol content, the U42 Saccharomyces uvarum would be a good candidate, as well as the MB15. Another important consideration is oxygen management, and some producers are applying micro-oxygenation. And one thing that I wanted to point out is that with ES454 and Vintage Red, what we saw earlier with the data that we presented was that they produce adequate quantities of acetaldehyde. And acetaldehyde is very important in encouraging these color condensations. So in a sense, it's more of like a biological color stabilization tool instead of applying microoxygenation. One thing that I didn't get into in this presentation because of the time is the importance of malolactic bacteria and strain pairing as well. So for those who are applying co-inoculation strategies or sequential inoculation strategies, hopefully in the future we can have a more focused webinar specifically on malolactic bacteria and Pinot Noir. Here we have a table just compiling all of the different chemical parameters that we analyzed for your reference. We also have some sheets as well, which have a little bit more detail on the specific nutrient requirements and characteristics of the yeast that we spoke about in this webinar. And if anyone has any questions or follow-up, please feel free to directly email me, and I'd be happy to supply you with some more in-depth information about what we went over today. So thanks everyone for joining and listening. And if anyone is interested, please feel free to email me at lauren.barrett@enartis.com to inquire about 2019 harvest trials. We're specifically designing some protocols, especially using some of our U42 Saccharomyces uvarum strain, and we're very excited to apply this in even more commercial trials with clients and see the effects. Here I have some of the citations listed, which I highly recommend going back and referencing. Again, if anyone has any questions or would like any more information, please feel free to contact me. Thank you all again for joining, and we'll catch you again on the next webinar presented by Enartis. Take care.